Hello, everyone. This is Professor DiPaolo, and this week we're going to be talking about hypothesis testing, which is a relatively complicated topic. So you're going to have to take your time to review the lecture, review the book, start doing the homeworks and process it. It's not something that comes immediately because it's a sort of a different way of thinking about the world. But I'm going to try my best to walk you through this and guide you to understand this difficult topic. So some of the learning outcomes for this chapter include understanding the logic of hypothesis testing. So basically you have a null hypothesis and you have an alternative hypothesis, and the goal is always to reject the null hypothesis and support the alternative hypothesis. To understand the idea of critical regions, which are basically cutoff scores in which you can then reject the null hypothesis. So if your test statistic lands in the critical region or goes beyond the cutoff score, you then reject the null hypothesis and support the alternative hypothesis. We're going to be talking about using the z-test to make decisions with regard to hypothesis testing. So this is like the first basic inferential test we're going to be doing. And we're going to follow this up in later chapters with t-test and nova and all of those things, correlation, etc. Talk about the two different types of errors, type 1 and type 2 errors that you can make while doing hypothesis testing. Understand the importance of effect size and compute a basic measure of effect size called Cohen's d. And then differentiate between directional and non-directional hypotheses. So basically in research, everything's about hypothesis testing. That you can't do research if you can't test hypotheses, and you have to be able to test your hypothesis using this system that we're talking about in this chapter, and this is called null hypothesis significance testing. This is the only way we can test hypotheses in psychology and mostly in science in general. Hypothesis testing is a method that uses sample data to evaluate the hypothesis about a population. So the hypothesis that you're formulating in your testing is always with regards to the population. However, we cannot measure the population, so we have to gather a sample, and based on that sample, test our hypothesis, and then based on our results, draw the inference from the sample to the population. So that sample supposedly is representative of the population, and whatever you find in your sample should hold to the population. However, there's a bunch of errors that can be made with that. Since we don't really know the population, we can make a mistake using the sample to draw the inference about the population. And that's where the type 1 and type 2 errors come in that we're going to talk about later in this chapter. So to conduct a hypothesis test, we need to state the hypothesis about the population. We then predict what we expect to happen based on our research or based on our experiment. So if we're doing an intervention, then we expect some kind of change to happen in our sample. So we expect our sample to be different than the original population, right? So if I'm doing some kind of tutorial with a sample of individuals, I expect that their performance would be different than the performance of people that never got the tutorial, which is the original population. Now, in order to do this, I have to obtain a random sample. Now, ideally, you would have a random sample, which means that every member of the population has an equal chance of being selected. In reality, in psychology, you don't always have a random sample, and that's okay. You can do this stuff without a random sample. It's better if you can get a random sample, but it's probably not likely. It's too time consuming and logistically impossible sometimes to get a random sample. So we use convenience sample a lot of times in psychology, and even though that's inferior to the random sample, we can still draw conclusions with the convenience sample. Convenience sample means we get who's available, rather than we randomly pick people from the population. It's just too much work, and sometimes it's just impossible to do that. when we gather the sample, regardless of what type of sample it is, we compare the results in that sample and we draw conclusions about the population. If the sample data is consistent with our hypothesis, we support our hypothesis. If the sample data is not consistent with our hypothesis, then we reject our hypothesis and we have to go start from scratch and figure out a new hypothesis. So here's a basic scenario for hypothesis testing. We know that the original population we're studying has a mean of 16 and a standard deviation of 3. So we do some kind of treatment or some kind of intervention by taking a sample from that population, doing the intervention, manipulating the independent variable, and then measuring it again after the intervention is done. We expect that that intervention or the treatment will change the mean of that sample. And that sample that we're looking at and we're doing the intervention on is representative of another population with a mean that is different than 16. So remember that the original population is the no treatment condition. So that represents what we're going to call the null hypothesis, that there's no effect of the treatment. So if there's no effect of the treatment, you would expect the sample to have a mean close to 16. However, if the treatment does work, you would expect the sample to have a mean that's significantly different than 16, not around 16. And that's the goal, is to sort of have that sample be far away from a mean of 16, because that means that the treatment most likely works. So based on our sample that we're taking from the original population, and then we're using the intervention on the sample, we are then going to infer that that sample after treatment or after the intervention represents a different population, a population where the treatment actually works, so where people are different than the original population that has a mean of 16. So the weird thing about hypothesis testing is just because your original population has specific parameters like a mean of 16 doesn't mean that there aren't other populations out there, right? So if there's a population of individuals that did not get the treatment, there's also going to be a population of individuals that got that treatment that are different. There are many, many, many different populations. You don't know where these populations are or what the parameters are of these populations. You don't know. So for example, if the original population has a mean of 16, there's an alternative population that has a mean of 17 or a mean of 18 or a mean of 20, etc. Right? The only goal for doing this kind of analysis in inferential stats is to say, does your sample belong to the original sample with a mean of 16, or does your sample belong to an alternative population with a mean different than 16? So let me repeat that again. The goal for the statistician is to determine, does my sample come from a population with a mean of 16 in this specific case, or does my sample come from a population with a mean that's not 16? So the mean could be greater than 16 or it could be less than 16. And that's going to happen after treatment, because if I'm doing the intervention, my goal is to have a different type of sample that doesn't belong to the original population with a mean of 16. I want to say that it's different in some way. It's better or it's worse, depending on my hypothesis. But I want it to be somewhat different. And the further away the sample mean is from 16, the more likely you can say that, no, it doesn't belong to the original population with a mean of 16. It belongs to some sort of alternative population that we don't know where they are. We haven't measured those people, but they exist. Just because we don't measure it doesn't mean it doesn't exist. It exists. We just don't know what it is. And that's the goal of the hypothesis test. So some of the steps to test a hypothesis. Step 1, state your hypothesis. Write it out. It has to be a testable prediction. So the hypothesis that you state has to be testable. If it's not testable, then it's not a hypothesis. It has to be testable. Set the criterion, step 2. Set the criterion for a decision. So how are you going to decide whether your sample data is different from your original population, right? So are you going to use what kind of values? And then this comes based on this comes down to what alpha level you set, because the alpha level is going to determine how far away from the original mean that the sample mean should be to reject the null hypothesis. So these are things that are kind of under your control. You can set that alpha level, although there are benefits and there are drawbacks for either raising it or lowering the alpha level. And the alpha level basically is the amount of error that you're willing to live with. More specifically, type 1 error, which we're going to talk about. So it's how willing are you, how likely are you to make a mistake, or how willing are you to make a mistake? And there's benefits and drawbacks, as I said, about making that error rate really smaller or very large. We then compute the sample statistics. So we take our sample, we compute the mean, we compute the standard deviation, and then we test our hypothesis. And we want to see, is that sample significantly different from the original population? And then we make a decision. So this all comes down to, what kind of sample, the size of the sample, the alpha level that you're setting, that you're making a decision based off of. Basically, how much type 1 error are you ready to live with? And that will determine whether you can say that the sample is different from the original population or not. And hopefully you reject your null hypothesis, which is what you want to do. The null hypothesis basically means that there's no effect, so you want to reject that. And that will support the alternative hypothesis, which is your hypothesis, basically, as a researcher. So the null hypothesis states that the treatment has no effect. There is no change, there is no difference, there is no relationship. Or another way of saying this, the independent variable that you're manipulating has no effect on the dependent variable that you're measuring. So the null hypothesis is something you don't want to support. You want to reject it all the time. Because it's basically saying that there's no effect or there's no difference. And as a researcher, you want to see that there's a difference or there's an effect. You never want to see there's no effect. So you always want to reject the null hypothesis. It's written as H sub 0. And once you reject the null hypothesis, you support the alternative hypothesis, which is your hypothesis. This is your research hypothesis, that there is an effect, that there is a change, that there is a relationship. Now, obviously, this is about the general population, but we're basing, our testing off of the sample. So we're using the sample to draw conclusions about the population. But we always want to reject the null and support the alternative, because the alternative is basically what we're looking to find out, like what we expect to happen, or what we want to happen. So there is an effect, there is a relationship. The independent variable works. Our research works. It's not a waste of time. That's the alternative hypothesis. So based on our sample data, so our sample mean and our sample standard deviation, but mainly our sample mean here. Based on our sample mean, we want to decide, is our sample mean close enough to the mean of the population that represents the null hypothesis, right? So where there's no effect. So if you go back to the previous example, that mean was 16. So we want to say, does our sample belong to that population? Another way to think about it is think of there's two populations. One population represents the null hypothesis, which basically means that none of your ideas work. There's no change, there's no difference. So whatever you did doesn't work. So that null hypothesis has its population. Those are people where there's no effect of the independent variable, this is what would happen. That's the null hypothesis population. And then there's the alternative hypothesis population. So this is the population where there is a difference. And obviously we want them to be as far apart as possible. So you have two populations, and you have to decide, does your sample belong to the population that represents the null hypothesis, or does your sample belong to the population that represents the alternative hypothesis? And the goal of that is to make sure that it's not close to the mean. So you do not want your sample mean to be close to the mean that's represented by the null hypothesis. The farther it is away from that mean, that means the more in the tail it is of that distribution, the more likely it belongs to the alternative population. And that's where you want it. So there's two populations. You have to decide, does it belong with the null or does it belong with the alternative? And these are your only choices. You can't say, well, I think it belongs to both. It doesn't belong to both. You have to make a decision. They're mutually exclusive. That means if you have one, you can't have the other. So you have to make a decision, either null or alternative. If it's null, you fail to reject the null hypothesis, obviously. And if it's alternative, you reject the null hypothesis. Now, by saying you reject the null hypothesis, does that mean the null hypothesis is false? No, because there's always a chance of making a mistake. There's always an error rate that we'll talk about, type 1 and type 2 error. So no matter what decision you make in statistics with regard to hypothesis testing, there's always a chance you're making a mistake. The goal is to minimize those chances, to keep them as low as possible, but there's always a chance. You will never prove nor disprove anything with statistical hypothesis testing. What you do is say it's very likely it's this case, and it's very unlikely it's that other situation. So you can use the words highly probable, very likely, highly improbable, very unlikely, but you cannot use the word prove, right? Or say that it's wrong, right? I like to use the word support. So when you reject the null hypothesis, you support the alternative hypothesis. You do not, prove anything. Supporting. You say that it's very unlikely that your sample belongs with the null hypothesis, so therefore it belongs to the alternative hypothesis. No proving, no disproving, no true, no false. It's all based on probability. Your alpha level or your significance level determines, how far your sample mean has to be from the null hypothesis, the mean, for you to say that it doesn't belong with that null hypothesis, that you can then reject that null hypothesis. If your alpha level is lower, that means you lower the chance of you making an error. It's going to take a bigger difference between the mean that represents the null hypothesis and the sample mean to say that they're different. Right? If that alpha level is higher, it's going to take a smaller difference between the null hypothesis mean and your sample mean to say that they're different. Generally in psychology, we use an alpha level of 0.05. It is rarely different than 0.05 as your alpha level. And there's reasons for that. In science, like in biology, if you were doing pharmaceutical work, you might want to lower your alpha level because you want to be really, really careful about making a mistake. Because if you made a mistake, if you're manufacturing drugs, you might produce tons and tons of drugs and spend so much money and the drug does nothing. You don't want to make that mistake. You want to be 100% sure, or as close to 100% as you can. You can't actually be 100%, but you want to be as close to that 100% positive that the drug works before you manufacture it and sell it. So in that situation where there's a lot of money involved and it's a huge decision, you want to risk lower amounts of error in rejecting the null hypothesis. So you might have your alpha level very, very low. But in psychology, 0.05 is almost always the alpha level that people use. And if you use something different, you can't use anything bigger than that, because people will completely reject your research. They won't even publish it if it's greater than 0.05. If you want to make it less than 0.05, you can, but there's problems with that as well. So 0.05 is generally the alpha level in psychology. And the alpha level determines the critical regions where you can then reject the null. So how big of a score do you have to have? How extreme of a score do you have to reject the null? Like how far out in the tails of the distribution does the sample mean have to be in order to reject the null? So the alpha level directly compares to that marker. We'll talk about this critical region. So here's what I was talking about, the population that is represented by the null hypothesis. So this represents only chance. So let's say the intervention doesn't work. Whatever you did in your research doesn't work. The independent variable has no effect. And the null hypothesis is true. So this represents the situation where the null hypothesis is true. There's variability here, though, because if you sample from a population, you're always going to get a different value for the sample. Now, most of those sample means are going to be close to mu, which is the mean of the population here, the middle of the distribution, mu. Greek letter, it looks like a little u. It's called mu. So most of your samples will be around there, but there's a chance that some of your samples can fall in the tails of this distribution. It's very unlikely, but there's a small chance that your sample means, if you randomly take samples from this population where there's no effect of the independent variable, so this is the population represented by the null hypothesis, there's a small chance that your means can be in the tails of this distribution. And that's where the problem of the error gets into it, right? Because ideally, what we want to show is that if the sample mean is in the tail of the distribution, you see those tails, those vertical lines here in the tails of the distribution, that you should reject the null and support the alternative. That's basically what we do with hypothesis testing. If your samples are in these tails, these critical regions, we reject the null hypothesis and we support the alternative. Because the likelihood that the null is true and you obtain a sample mean that's in the tail of these distribution, right, is very low. So if the null is true, you're not likely to get this, but you could. And that's where the error comes in again. You could get this. It's a very small percentage chance. But there is a small chance that the null could be true and you could get an extreme value in these tails. And that would basically mean that there was a difference, but that difference is due to chance. It's due to what is called sampling error. Just random chance, random variation. That's a really small probability. But in that positive tail, the tail to the right, it's about 2.5% chance for that happening. Tail to the left is about 2.5% chance. Because remember, we want to keep it at 5% total. If the alpha is 0.05, that's 5% of an error rate that we're willing to accept. So it's 2.5 in the positive tail and 2.5% in the negative tail. So there's a small probability that if the null is true, that means that your research doesn't work out, that you could still get an extreme score by chance alone. So you have that possibility. However, the way we do hypothesis testing is if the mean is in the tail, we reject the null and we say that there's a very unlikely chance that this sample belongs to this null hypothesis population, and instead that the sample belongs to some alternative situation, some alternative population, where the treatment works, where the independent variable works. this represents, what I'm showing on the screen represents the null. It represents a situation where nothing works. The treatment doesn't work. There is a situation to the right. So if you were to imagine another curve drawn to the right of this curve here on the screen, that's an alternative population where the treatment does work. Or if you imagine a distribution to the left of this null hypothesis population, that's also a population where the treatment works. So anything in the tail is thought to belong to an alternative population to represent the alternative hypothesis. But there's still a chance that it could represent the null, and that's the error rate. So there's no way to make this error proof. In order to reduce the error, we can make the tail really small. We can make the tail really, really tiny and say it has to be in this little tiny, tiny portion of the tail to be able to reject the null. But that's not good either because that's too restrictive. If we make the tails here, the critical regions really small, you're not going to reject the null many times, and many times it's going to be a mistake the other way. Many times there's going to be an effect, that they're in reality, that your research works, but since you made it so restrictive to actually find that effect, you're not going to find it. So the 5% is kind of a balancing point, the 0.05 for the alpha. It makes it so that there's a small amount of error, but it doesn't make it impossible to reject the null hypothesis when you should reject the null hypothesis. So I know this is a lot of jargon, but it has to kind of sink in. It's going to be a slow process. You're going to have to really digest it because it's completely different than a lot of the things you've already talked about in your prior experiences with courses. Hypothesis testing is unique. I'm not saying it's the best thing in the world. I have like mixed feelings about the system in general, about hypothesis testing, but there are merits to it. It's been used forever, and people are really resistant to changing the system. So this is the way I see it, science being conducted for the foreseeable future. Now, if we're looking at these critical regions or these tails that you see cut off here, they correspond to a certain value of your test statistic. And since we're talking about Z, the normal distribution here, these tails for 5%, this is an alpha value of 0.05, the critical values for these tails is 1.96 or negative 1.96. That means that your sample mean, when converted to a z-score, which you did in the last chapter, has to have a value greater than 1.96 or less than negative 1.96 for you to reject the null hypothesis. So you need a sample that has a z-value greater than positive 1.96 or less than negative 1.96 for you to reject the null hypothesis. That means that your sample mean has to be in these tails, either the positive tail or the negative tail. And this 1.96 is a general rule for z-score. So anything that has a z-score greater than positive 1.96 or less than negative 1.96, that's seen as a positive, right? Because now you can reject the null. If it's less than this, if it's in the middle of the distribution, then you can't reject the null. Then you fail to reject the null hypothesis. So only values in the extreme tails allow you to reject the null hypothesis when you're looking at the test statistic here. And for 0.05, if you're looking at both tails, this is called a two-tailed test or a non-directional test. So if you're doing two-tailed or non-directional tests, you need 1.96 and negative 1.96 as your cutoff scores for the critical region. Sometimes it's called a critical value. 1.96 and negative 1.96, and you should memorize those values because they're important they're always going to be the same for Z. Those critical values here, 1.96 negative 1.96, always going to be the same for Z, no matter what the problem you're doing. So let's look at some of these questions. A sports coach is investigating the impact of a new training method. What would the null say? Remember, the null is no effect. So A, the new training program is different than the existing one. Well, that's showing an effect. It's a non-directional hypothesis. It's showing an effect, though, so it can't be that. B, the new training program produces results similar to the existing one. So it's saying there's no difference. That's what the null hypothesis always says. There's no effect or there's no difference. So since B says there's no difference because it's similar, then it has to be B. That is the answer. The answer is B. The new training program produces results similar to the existing one. That's the null hypothesis. Let's look at a couple of these. If the alpha level is decreased, the size of the critical region decreases. Well, if you decrease alpha level, you make it much harder to reject the null hypothesis. So in order to make it much harder to reject the null hypothesis, you've got to make the critical region also much less, right? And the second one, the critical region defines unlikely values if the null is true. That is the case because those are the tails. So if you end up in the tail, then the null is most likely not true. And that's what we got here. So if you lower alpha, you shrink the critical region. You make it harder to reject the null hypothesis. That's a key point moving forward. That's why you don't like to lower alpha too much. Keep it at 0.05. So now that you have your hypothesis set up, your null and your alternative, you can collect data. So you've set up your hypotheses, the null and the alternative. You set your alpha value, so you have to have your decision criteria. The alpha value determines your critical region, your cutoff scores. You do not want to collect data first and then look at your data and then draw up your hypothesis. This is not the way you want to. This is not good science. Because now you're not objective. Because now you're looking at the data and you're changing your hypothesis. It's kind of cheating. The hypothesis should always come before the data. Make sure that everything is done before the data. And I wouldn't look at the data until all the data is collected, because that might, change your objectivity in the study. If you don't want to run the whole experiment at the beginning and you want to test it out, then run a pilot study. So run a study with 20 people and see what you get on the pilot study. If the pilot study turns out to be a mess, then you don't have to run the full study, and it saves you time. So if you're not 100% certain and you're not confident, I like to run a pilot study for everything, just to see that I know what I'm doing and I know what to expect. Is there problems with the study? So you run this short pilot study, this practice study that doesn't count. You're not going to publish it. You're just using it to look at the data to make sure the study is running correctly. And then once you have the pilot study and you're satisfied, and the pilot study shows data that seems to support your hypothesis, then you run the full study. That's probably the most objective way to run research, rather than not hypothesis or changing your hypothesis after you collect your data. That's not ethical. And there's going to be times where you have a hypothesis and it's not supported, and your whole research is a waste. And that's part of the research process. Not all research studies work out. I would say that more studies don't work out than actually do work out. So that's why research can be great, but it could also be annoying in that there's many dead ends that you find. So once you have your data, you can then compute your z-test. So z equals the sample mean, which is m, minus the population mean, which is mu, divided by sigma sub m, which is the standard error of the mean. So that's the sigma population standard deviation divided by the square root of the sample size. And we hope that our z value is large enough. In the previous case, we used the cutoff value of 1.96. We want our z value to be bigger than 1.96, or in the negative case, less than negative 1.96. That's the goal. So if z is in that critical region, that means it's more extreme than the critical value that you set based on your alpha level, you reject the null. And if z is in the middle of the distribution, you fail to reject the null. Simple as that. There are errors though. Sometimes you reject the null hypothesis, and in reality, you made a mistake. So sometimes you reject the null hypothesis, and in the population, the null hypothesis is true. And sometimes you fail to reject the null hypothesis, but in the population, the null hypothesis is false. So those are mistakes. And these mistakes are made because we're taking a sample and we're drawing conclusions about the population. We don't know what's going on in the population. And so it's very easy to make a mistake. We're using these rules applying these rules to our samples. And, our alpha value says that there's going to be a chance that we've made a mistake with our samples in terms of what's going on in the population. You're never going to be 100% correct or 100% incorrect. There's always a chance that you're making a mistake. Every time you test a hypothesis, there's always a chance you've made a mistake. And you might see this as a flawed process, but when you're basing things on probability, there's never going to be a probability of 0. There's never going to be, which makes things impossible. There's never going to be a probability of 1, which makes things certain. There's always a chance of basically anything happening. So there's a chance you made a mistake. This is not physics, where there's laws, where every time you do something, you don't need a hypothesis because every time you drop something, it falls to the ground, right? You don't need a hypothesis to test gravity. You don't have to say, well, I want to test if gravity actually exists on Earth. So the null is that, gravity doesn't, there's no gravity, so therefore everything floats in the air. And the alternative is that there is gravity, so when I drop something, it falls to the ground. You don't need to test that hypothesis, because every single time you drop something, it's going to fall to the ground. It's not going to float in the air. So those are certainties. Those are laws. Laws of thermodynamics are laws. The melting points are laws. You heat a particular metal up to a certain temperature, it's going to melt. If you boil water at 220 degrees Fahrenheit, 100 degrees Celsius, you're going to evaporate the water. If you lower the temperature to 32 degrees Fahrenheit, 0 degrees Celsius, you're going to freeze the water. You don't need hypothesis testing for this. This happens every single time. But in psychology, you don't have these situations. You don't have laws. So if you don't have laws, and you can't have laws with human behavior, it's too complex. Which is both simultaneously the exciting thing about psychology and also the most frustrating thing about psychology is that, yeah, there's so many interesting things that we don't know about how human beings behave. But we're never going to be 100% certain of things because we're always going to test hypotheses and there's always going to be chances of making a mistake. So you got to keep that in mind in terms of hypothesis testing. There's always a chance of an error. In a type 1 error, a researcher rejects a null hypothesis that is actually true. So you've made a mistake. You've rejected a null and you said the null is not likely, so you support the alternative. But in the population, the null is actually true. So you made a type 1 error. If you set alpha to 0.05, you are allowing for 5% type 1 error rate. And you don't want to lower alpha too much because if you lower alpha, you're going to increase what we're going to talk about, beta, type 2 error. So you want to keep alpha at 0.05. But you're always willing to live with a 5% chance that you incorrectly rejected a null hypothesis. And you publish this, and it's out there for everybody to see. You say, we found these results. But there's still a 5% chance. I mean, if you're using 0.05 as your alpha value, there's a 5% chance you made an error. Now, that could be smaller because if you use a computer program, you could find the actual probability of the type 1 error. So a computer program like Excel or SPSS will give you what's called a p-value. And the p-value will give you the probability of a type 1 error. So you can actually find the exact probability that you made a mistake, which is the benefit of using computers. By hand, you can't do this. You can only do this with a computer. And that tells you exactly where it's at, right? So you could be at like, at 4.5% error rate, but you could also, have a really big effect and be really small error rate. It would be less than 1%. But there always is going to be some percentage that you're making an error, that you're incorrectly rejecting the null hypothesis. And you get excited. You say, my research works, my idea works, my intervention works. And you might believe that it works, but it could be type 1 error. It could just be a mistake. And there's always going to be these kind of errors because you cannot measure the entire population. So that's the downfall of hypothesis testing. There's always these small probability of making an error. Type 2 error is the opposite. This is when you fail to reject the null hypothesis, but you should reject it. So that means that you didn't support your idea, but you should have. In the population, your idea works, but in the sample, you just didn't find it. And one of the biggest reasons for this, for not rejecting the null hypothesis when you should, is that your sample's too small. So if you have a small sample size, you're going to have a much higher likelihood of having these type 2 errors, where your hypothesis is supported. In the population, your hypothesis is real. So in the population, your idea works. But in your sample, you can't find this effect. You can't show that your idea works because you have such a small sample. So these are hard to actually identify because if you run the statistics and you fail to reject the null hypothesis, there's no way you can know that you've made a mistake. And the reason why you don't know if you made a mistake is because you don't know what's going on in the population, because you can't measure the population. Same thing with type 1 error. You reject the null hypothesis in type 1 error, you think you've done a good job. And maybe you have, but there's always a small chance that you've made a mistake. And you'll never know if you made the mistake or not. Now, someone could try replicating, and if they can't replicate, then maybe that calls into question your study. But what if someone doesn't replicate your study? Then how do I know that this is the state of the world, that your idea works in the world, in the population that we're studying? I don't. I mean, I could say that there's a high probability that it works, but I can't be 100% sure that you're correct. And that's the frustrating thing. It's all based on probability. And there's always going to be a small chance of having a type 1 error. And there's probably a little bit larger chance of having a type 2 error because of the sample size issue. Now, if you have a large sample, type 2 errors will be less likely. But with a small sample, there's a good chance you could have type 2 error. Also, if you decrease type 1 error, you always increase type 2 error. So if you decrease alpha, which is type 1 error, you can increase beta, which is type 2 error. Type 2 error is called beta. So one affects the other. So if I lower alpha, I increase beta. If I increase alpha, I decrease beta. That's why 0.05 is the magic number once again, because if I set alpha at 0.05, I'm kind of averaging out the type 1 and type 2 error. I'm trying to make them equal, relatively equal. I don't want too much type 1 error and I don't want too much type 2 error, so I set it at 0.05, and that's a pretty, a balancing point. And here's a slide describing the two different types of error. So in my sample, if I reject the null, and if the null is true in the population, I've made a type 1 error. In my sample, if I reject the null, and the null is false in the population, then I've made a correct decision. I rejected it when I should reject it. I made a correct decision. So if I reject the null, and the null should be rejected, and it's false in the population, I made a correct decision. If I fail to reject the null, and the null is true in the population, that means there's no effect in the population, then I've also made a correct decision. And if I fail to reject the null, and the null is false, which means I should have rejected it, then I've made a type 2 error. So this table is important for you to understand and go through. And here's a picture of what happens if I decrease alpha. So if I set alpha at 0.05, two-tailed, you see that I have a critical value of 1.96 for Z. If I decrease alpha and make it more stringent, so if I want to really be careful about type 1 error, and I want to lower type 1 error, if I move alpha from 0.05 to 0.01, look what happens to the critical value. It goes up. So it goes from 1.96 to 2.58. So now it's a lot harder to reject the null because alpha's gone down. So it makes it much harder to reject the null to find this effect. And if I make alpha ridiculously small, if I make alpha of 0.01, then I've inflated Z to 3.30. So now it's almost impossible to reject the null hypothesis. That's why we want to go to 1.96, which is 0.05 for alpha. So to summarize hypothesis testing, we state our hypothesis, we select the alpha level, we find our critical region or critical values of Z, or whatever the test statistic is. We then collect data, we compute the critical value, we compute the test statistic, I should say, which in this case is Z. And then based on where Z is relative to the critical values, we determine if we should reject or fail to reject the null hypothesis. If we reject the null hypothesis, we call it statistically significant. So statistically significant means that you've rejected the null hypothesis. And so that basically means it's not due to chance. Your result is not due to chance, it's due to a real treatment effect, or the real effect of an independent variable. Now, if you see this in the literature, you're likely to see the word statistically significant, which means that you've rejected the null hypothesis. And generally, it's less than 0.05. You may see the exact p-values. So the computers report the exact p-values. You might see those in a journal article. If there's a large difference between your sample mean and the population mean, then you're going to have a large z-score, and you're more likely to reject the null. Also, if there's more variability in the population, that means if the variance and standard deviation are larger, you're going to have a larger standard error, and you're going to be less likely to reject the null hypothesis. So more variance equals harder to reject the null. And sample size, if you have a bigger sample, the bigger the sample, the smaller the standard error, and the easier it is to reject the null hypothesis. So it's hard to change the standard error. It's easy to change the sample size. So if you cannot reject the null hypothesis, and it seems that you're close, like you're going in the right direction. If that's the situation, then just add more people. Increase the sample size. If you increase the sample size, you make it much easier to reject the null hypothesis and then conclude that you have a statistically significant result. Now, if I'm using the z distribution to test the hypothesis, I want to try my best to use random sampling, although sometimes I can't. Like in psychology, it's very hard. We use convenient samples. I also want to have independence of observations, which is easy to do with random sampling, but uh, with sampling in a convenient sample, it may not be that. It may be very difficult because what happens is if you put someone in your sample, you don't put them back in the pool to draw again, right? Because if you only want to have one person, uh, you know, execute be in your experiment once, right? You don't want to have the same person in your experiment more than once. So if that's the case, you're going to have to take them out of the population pool. You can only sample them once. You can't sample them again and again and again. So by doing that, you are changing the independence of the observations. So once I take someone out of the population, I do not put them back in, and therefore the probabilities change. Is that a big deal? No. That's the same thing with the random sampling. Is it a big deal that you don't use random sampling? No, not really. It's better to use random sampling because random sampling will get you, for the most part, independence of observations, but you don't need it. And the reason you don't need it is because a lot of these hypothesis tests are robust. So you may not meet all the optimal criteria to use the test, but it doesn't matter. You're going to get the same results. You're still going to get good results, right? So just because you don't meet all these assumptions doesn't mean that you can't use Z. Now, the one thing that you want to really meet is this, where it says normally distributed sampling distribution. That's key. And how do you get that? Well, we talked about central limit theorem last time. You get that by having a sample size of 30 or more. That guarantees it. Or by having the population, the null hypothesis population, to have that normally distributed, which you may or may not know. The easiest way to get it is make sure you have a sample of 30 or more. That guarantees a normal distribution. If you don't have that, then you may not be able to use the z-test. So let's say you have 10 people and you don't know if the population is normal, right? You don't know the population at all. You might think the population is skewed. Well, if that's the case with 10 people, you can't use z-test because you can't use the normal distribution. So that's probably the most important assumption on this list is you want to make sure that either your sample size is big enough, 30 or more, to get you a normal distribution, normal sampling distribution, or you want to make sure that the population that you're drawing the sample from is normally distributed. If not, then you can't use Z, you have to use something else, and you're probably going to be in trouble. Let's look at these questions here. A researcher uses a hypothesis test to evaluate the null hypothesis that the mean is 80. So H0 is null hypothesis, mean of the population is 80. Which factors is most likely to result in rejecting the null hypothesis? Well, in order to reject the null hypothesis, it's best to have a bigger sample size and to have smaller variability. So in this case, we want a big sample size and we want small variability. And if we look at this, we have 10 for standard deviation, we have 5. So it'd be better off having 5 because that's smaller in terms of the variance. And we want a bigger sample size, so comparing the 5s, you have 25 and 50. So B would be the best because you have the largest sample size and you have the smaller variability. And that's obviously the answer. Now, can you control the variability? It's hard to control the variability. It's easy to control the sample size. That's why if you want to really reject your null hypothesis, you want to get a bigger sample. The bigger the sample, the better position you're going to be in to reject the null hypothesis. And that's really because that n, that sample size, is in the denominator. If you look at the standard error formula, it's sigma divided by square root of n. So if that n gets bigger, then that standard error is going to get smaller. And if the standard error is smaller, you're going to have a bigger z value. So the easiest way to do that is increase the sample size. Just use more people or more objects or more whatever you need. Increase the sample, you'll be in good shape. True or false? An effect that exists is more likely to be detected if n is large. Well, that has to do with, yeah, that's what I was saying before. If your n is sample size is big, you're more likely to have a bigger z-score. Second one, an effect that exists is less likely to be detected if sigma is large. Well, once again, if sigma is large, the standard deviation is large, your standard error is going to be relatively large, and you're going to have a smaller z-value, which is not good. So you want smaller standard errors, which, smaller population standard deviations will lead to smaller standard errors, right? And you want bigger sample size, which leads to smaller standard errors. So true. A larger sample produces a smaller standard error and a larger z-score. That's the easiest way to control is the sample size. And the second one, a larger standard deviation increases the standard error and produces a smaller z. This is just based on the formula. So you want to have smaller standard deviations and larger sample sizes, and that's going to get you better results, and that's going to allow you to reject the null hypothesis. But by far the easiest one is just more people. Increase the sample size. We've been talking about non-directional tests. So if you want to look at critical values in the positive and negative direction, you have what's called a non-directional or a two-tail test. But if you're only looking in one direction, right, so if you specify the direction of the effect in your hypothesis, your alternative hypothesis, you're going to have a directional hypothesis. You're going to have one tail. And the one tail is statistically better to use if you are certain the effect is going to only be in one direction. If you're not certain of the direction of the effect, use two tails, non-directional. But if you're 100% certain that you're going to have an increase or a decrease, then use the directional, because you'll have an easier chance of rejecting the null hypothesis. So if you're sure of increase or decrease, use a directional hypothesis. If you're just looking for a change or a difference, use a non-directional hypothesis, right? So only if you know the direction for certainty do you want to use directional. And in research, in terms of publication, no one really uses directional, really. Most of the stuff is non-directional. And if you use directional, you better have a really good reason for using it. Not other than, well, it's easier to reject the null hypothesis with directional hypotheses. That's not a really good reason for using it. Most researchers want to use non-directional because when you publish, there is a lot of skepticism about using directional tests. So only if you have the specific direction of the treatment effect can you use the directional. And you better be 100% sure of the direction. You have to either specify an increase or a decrease in the population as a result of the treatment. And there are some cases like, I've done meditation studies and I specify directional hypothesis because I expect that meditation will decrease anxiety. That's my hypothesis. Now, if meditation increases anxiety, I'm not going to be able to find that. If I do a directional hypothesis, I won't be able to find that effect if it actually increases anxiety. So I'm only looking at decrease. If I look at decrease, I have to only look at decrease. I can't look at either one. So if I want to look at both increase and decrease, I want to use non-directional test. If I know 100% certainty that it's going to go in one direction or the other, increase or decrease, then I can use a directional test. But if you're not 100% sure, play it safe, use a non-directional test. Here's your directional test for 0.05. Remember the previous slide that showed a non-directional test for 0.05? And you saw that the critical value for z was 1.96 and negative 1.96, right? So that was with non-directional, that was two-tailed. And the z value was 1.96, negative 1.96. Look what happens when we do one-tailed, a directional test. The z value is no longer 1.96, it's all the way down to 1.65, which makes it easier to reject the null hypothesis. So you can see based on just the critical value of z here, 1.65, that it's much easier to reject the null hypothesis when you use a directional test versus a non-directional test because the z-score criteria is lower. Here it's 1.65, before it was 1.96. However, make sure you're 100% certain that you know the direction of the effect. Because if I'm looking in the positive tail here and I get a result in the negative tail and I'm doing a directional test, I can't find that result in the negative tail because I'm not looking there. I'm only looking in the positive tail. So if I get a result in the negative tail, it doesn't exist if I'm doing a directional test. So you need to be 100% certain that the effect is going to go in a particular direction. Otherwise, you might end up screwing yourself out of something that's interesting. And a lot of times we hypothesize one thing and the opposite happens. And if I'm looking at a directional test, I'm not going to find the opposite happens, in this case, because I'm only looking at one direction. So my advice, and pretty much every way I run my own studies, is I use non-directional tests for everything. Just because it's very easy to get criticized for using directional tests because they're easier to reject the null hypothesis with the directional tests. And people think, well, you're only using a directional hypothesis because you can reject the null hypothesis that way. Especially if let's say your z-score is like 1.66 and you can reject the null with a directional test, but you cannot reject the null with a non-directional test, and you decide to use a directional test. Someone that's looking at your paper, that's reading your manuscript, is going to say, wait a minute, are they using a directional test because they can't reject the null if they do it the other way with the non-directional test? They're going to get suspicious. So you better have a damn good reason why you're using a directional test. And it better be, argument proof that no one can criticize you for it. Because if they can't criticize you for it, they will criticize you for it. Especially if it's the only thing that's making you reject the null hypothesis. Is the fact that you're using a directional test over a non-directional test. So a one-tail test makes it easier to reject the null hypothesis. You require a smaller difference between the sample mean and the population mean, where you need a bigger difference with the two-tail test, which is what I just explained. However, you should almost always use two-tail tests unless you have 100% certainty and a good reason for using a directional test. And in my opinion, it's not even worth it. Just use the two-tail test because you're going to get so much criticism from one-tail test, especially if it's an idea that someone else doesn't believe in or doesn't accept, and you use a two-tail test, they're going to be all over you. They'll criticize you for it. They may even make you change it to publish. They may make you do the non-directional test. There's a strong bias against directional hypothesis tests for whatever reason. I think because people kind of take advantage of them. The most popular example of this was the whole psychic powers study that was run by Daryl Bem a few years ago, I think around 2010 maybe. He wrote a paper showing that people had ESP, that they could read other people's minds in a different room. And he published it in a very prestigious journal. He published it in the Journal of Personality and Social Psychology. And what they found when they looked at his research and it was published, they found that he used a lot of directional tests, hypothesis tests. He didn't use non-directional tests. And people killed the guy and said, this is a hack job. This guy used directional tests, just to be able to support his hypotheses. We don't believe anything he says. He got criticized so severely. I've never seen someone a researcher criticized like this. Daryl Bem, BEM, in his paper on ESP, extrasensory perception. You can look it up if you want to read about it. Let's look at a few more of these problems. A researcher is predicting that a treatment will decrease scores. If they use a directional test, then the critical region would be, if they're looking for a decrease, where's the critical region going to be? The right or the left-hand side? Well, the right-hand side of the curve is increase, so left-hand side of the curve is decrease. So if they're looking for a decrease and it's directional, they're only going to be looking to the left. So you have to look for the answer to the left, and that's going to be B, to the left. measure it. If I was looking for an increase, I'd be looking in the right tail. If I'm looking for a decrease, I'm looking in the left tail. If I'm looking for a change, I'm looking in both tails. That would be non-directional. Now, we talked a little bit about significance testing and the p-value and the one and two tailed hypothesis, directional, non-directional. Let's talk about something else called effect size. Effect size is the effect of the independent variable or the treatment independent of sample size. And the reason why this is important is because you can reject the null hypothesis. So you can get a statistically significant effect just by inflating your sample size. So let's say that you inflate your sample size to 1,000 people. You have 1,000 people in your study. You could have a really, really small effect in your study. But if you have 1,000 people in your study, it's going to be statistically significant. What that means is that the large sample size can inflate the importance of your findings. Because you're going to say, look, I found my research works that this new behavioral intervention that I developed, it leads to a great amount of weight loss. So now I'm going to sell it on the market and make tons of money, right? You developed this weight loss intervention, you used it on a lot of people, and let's say you found that this weight loss intervention leads to a loss of 1 pound. Now you might say to yourself, well, if it only causes you to lose 1 pound, how is that important? Well, that's a good question. Does it work? Well, the answer is if I run that intervention on 1,000 people in my sample, it's going to say that that 1 pound difference is statistically significant, which means that it's not due to chance. It's due to your intervention. So that 1 pound weight loss is due to your intervention. And you could say as a researcher, my intervention works. You know, my intervention causes weight loss. So I'm going to sell it now, and I have the study to show that it works. And do this intervention, and you're going to lose weight. Now, just because it's statistically significant means it's not due to chance. It means that it actually does work. Doesn't mean it works well. So I would say a 1 pound weight loss doesn't mean it works well, right? The effect is very small. It might be statistically significant. That means it might not be due to chance. It might be real, but it's really, really tiny. And the only reason you found it to be statistically significant is you used a huge sample size, like 1,000 people. Some people use even more than 1,000 people. They use 5,000 people. Well, with 5,000 people, pretty much everything is going to be statistically significant. But how important is the effect? How big is the effect, regardless of sample size? And that's what effect size tells us. It tells us how strong is the effect of the treatment or the independent variable, regardless of the sample size. So this is really good when you have inflated sample sizes and you want to see really how important is your research. Rather, other than it's important enough that 1,000 people made it statistically significant. And Cohen's d is a very simple way of comparing means that allows you to see how big the effect is. So you calculate Cohen's d by looking at the mean difference, so the mean of the treatment minus the mean of the no treatment, which is the null, right? So basically, if you're using one sample, it would be the mean of the sample, which got the treatment, minus the mean of the null hypothesis, which is basically the people that got nothing, divided by the standard deviation of the population. And when you do this calculation, you're going to have a value that's between 0 and 1. And if the value is close to the 0, so 0.2 is a small effect, 0.5 is a medium effect, and 0.8 is a large effect. And if you have a small effect and you have a big enough sample, you'll still have statistical significance. But the effect will be very small, and you'll say, okay, your intervention works, but it probably only works because you have 1,000 people. It's not a big deal. It's a small effect. So these effect size measures are important, especially when you're dealing with inflated sample sizes. which you come across more often than you think, especially on the internet. So a lot of internet research, you're getting huge sample sizes. And so be very careful about what conclusions they draw. Always look for effect size. When you have a big sample, double check that they put the effect size in there. Chances are they haven't. Chances are they haven't. So, but be careful. And here's another example from your textbook about what I'm talking about. If there was a 15-point difference on the SAT after some kind of intervention or some kind of program to boost your SAT scores, you might say 15 points, that's a big deal. But if you look at the standard deviation of 100 and you want to find the effect size, you find that 15-point difference and you put it over 100, and the effect size is only 0.15, which is quite small. So that's a really small effect, 15-point increase in the SAT. But if you look at that 15-point increase when it comes to IQ, now the standard deviation is much smaller, it's 15. So the 15-point increase is divided by 15, and you get a effect size Cohen's d of 1. So now this is a huge effect, because it's actually an entire standard deviation, right? So the effect size is basically the number of standard deviations that the intervention provides, that you benefit from. In the first case, it's only 0.15. That's less than 1/5 of one standard deviation. That's really small. In the second case, it's 1. That's huge. It's a huge effect. That's a whole entire standard deviation. So the treatment here boosted your score, your IQ score, by one whole standard deviation. That's amazing. In psychology, you're dealing with smaller effects. So if you get to small to medium, that's what you're mainly dealing with. Very rarely do we get large effects in psychology. Because once again, it's hard to measure things. It's hard to make huge differences with relatively small samples. You don't see too many like 0.8 or higher effect sizes in psychology. I mean, they exist, but just not very common. More true false. Increasing the sample size will increase the effect size. Well, sample size increases significance, but does it increase effect size? No, because effect size is the magnitude of the treatment independent of sample size. So it doesn't matter what you do with the sample, it will not change the effect size. So that's obviously false. And the second statement, larger differences between the sample and the population mean increased effect size. Well, that's how you calculate effect size. It's the mean of the sample minus the mean of the population. So if that difference gets bigger, then by default, the effect size is going to get bigger, because that's basically the numerator of the Cohen's d fraction that you compute. So large differences between the sample mean and the population mean will lead to greater increases in effect size. That's true. The last topic is power. And power is the probability to correctly reject the null hypothesis. So it's the probability that when the null hypothesis is false, that you reject that false null hypothesis. Another way of saying this is it's the probability that you support your hypothesis when your hypothesis really exists in the population. So your idea works in the population, and you actually found your idea to work in your sample. This is very important, because why do research if you cannot find the effects in your sample that are in the population? Then why do research at all? There's no point, right? There should be a very high probability that if your ideas work out, if your hypothesis is supported in the population, which you don't know, but if it works, you should be able to find that in your sample. There should be a very high probability of doing that. Otherwise, there's no point in doing research, right? Because otherwise, you test your sample, you would fail to reject the null, right? You would say, my idea doesn't work, but in the population, your idea does work, and then you'd be really frustrated you wouldn't even know this, and you'd have what's called type 2 error, and you know you'd be a miserable researcher. I had this great idea, and then it didn't work. And if you knew that it actually did work and it was just a problem with your sample, you'd be frustrated to all hell. So power is the probability of correctly rejecting the null hypothesis. It's also known as it's calculated as 1 minus beta, where beta is the probability of type 2 error. So it's 1 minus type 2 error. Ideally, we want power to be 80% or higher. Otherwise, there's no point in doing research because you're just wasting your time. You want it to be 80% or higher because we want it to be there's an 80% chance that if the result is real, if your hypothesis is supported, that you actually find that in the sample, right? So you're not wasting your time. If your power is like 20%, and there's only a 20% chance of detecting the difference in the sample, where that difference really exists in the population, then what's the point of testing the sample? There is no point. And so researchers can calculate power before they run the study. So they can say, okay, I want 80% power. How many subjects do I want? Given the anticipated effect size of my independent variable, how many subjects do I want? How big should my N be to get 80% power? That's a very common question that researchers use, and statisticians tackle all the time. The goal is to get 80% power or higher. Here's an example of a study with low power. So in the null hypothesis, the mean is 80. You see that on the left here, the curve on the left. The standard error is 5, right? And that's because the sample size is small. Look at the sample size is only 4. So if the sample size is 4, the population standard deviation is 10, and the standard error is 5. So the population standard deviation is moderate. 10 is not that big, but with a sample size that small, the standard error is kind of big, 5, right? We'd like that to be smaller. Now, the intervention leads to a difference of 8 points. So the treatment condition has a mean of 88. So there's a difference of 8 points. But you see how the two curves overlap? The two curves overlap a lot, and that makes this difference of 8 points very hard to find. And if you see the shaded portion to the right where it says reject the null, that's the probability of correctly rejecting the null hypothesis. That's power. And you see that's pretty small. It's like 30-something% here. It's less than half of the curve, right? That's not a good study. And the reason why it's so small is because that the power is so low is because these two curves overlap. And the reason those two curves overlap, there's twofold. There's a difference of only 8 points between 80 on the left and 80 on the right as the mean. 8 points is not a huge difference, but if you combine that with the standard error of 5, so the standard error of 5 means that there's a lot more variability. So the curves are kind of wider, they overlap. If the standard error is smaller, the curves become more narrow and they don't overlap as much. And when the curves don't overlap as much, a difference of 8 can show much higher power because the variability is much smaller. And if you decrease variability, you increase power. Now, it's hard to decrease variability. You can't directly control that. I mean, you can alter the measurement, try to make a better, more sensitive measure. A better measure might decrease variability a bit, but it's really hard to decrease variability. What you can do instead of decreasing variability is you can increase sample size. And if I increase sample size, the standard error of the mean is going to get smaller. And if the standard error of the mean is going to get smaller, these two curves are not going to overlap as much. And if these two curves don't overlap as much, the power is going to be bigger. It's going to be much easier to correctly reject the null hypothesis. So this comes back to one simple thing: increase the sample size. You won't have to worry about this situation on the screen here if your sample is big enough. But with a sample of 4, you're going to have big, wide distributions that are going to overlap. If you increase the sample size, they're going to get much more narrow, and this difference of 8 points is going to look much bigger because the distributions are going to be much more narrow because of the increased sample size. So as I was mentioning in the previous slide, if I increase effect size, that means the mean difference, right, between the null and the treatment, right, between the treatment sample and the null hypothesis population. If I increase the sample size, I increase power. That makes sense. If there's a bigger effect, there's easier chance of finding it because the effect's bigger. However, if I increase the sample size, I also increase power. So if the sample size goes up, there's a better chance of finding the difference and rejecting the null hypothesis. And that's the easiest one to control. It's hard to control effect size because that's basically how strong your intervention is. That's difficult. It's hard to control variability. It's easy to control sample size. So that's by far the easiest way to increase power is increase sample size. Use a one-tail test, which is a directional test, compared to a non-directional two-tail test. But once again, everybody else knows you're doing this, so they're going to get angry if you're doing this only to increase power. That's why I talked about the Daryl Bem story. You know, people thought he was using a directional test just to increase power, not because it was justified, which is why people like two-tail tests. They don't like directional tests. They get very suspicious. Why are you doing a directional test here? Are you doing this only to reject the null hypothesis? Because it increases power. So I pretty much avoid one-tail test almost all the time that I try to publish things. I try to stick solely to non-directional tests, two-tail tests. Because a one-tail test has increased power over a two-tail test. It's easier to reject the null hypothesis. You can also decrease variability. That's not on this list, but if you decrease variability of the population, you increase power. The problem is it's very hard to decrease the variability of the population. So it's not even something to list here because you really have no control over that. Decrease power, you can also, if you reduce the alpha level, you decrease power. So if I lower my alpha level, power goes down. If I raise the alpha level, if I make it bigger, power goes up. You can't make it bigger than 0.05 though. 0.05 is the largest you can make it. If you make it bigger than that, forget it. People will not take your research seriously. So you got to keep it at 0.05 really. So you can't really make it easier that way. You can make it harder though. If you make it 0.01 to make it much more stringent, you're going to decrease power by a lot. That's probably not a good idea. So that's why we keep it at 0.05. And obviously, if you use a two-tail test, you decrease power compared to a one-tail test. But once again, the state of the field really not requires, but expects you to use two-tailed non-directional tests. And if you use a one-tail test, you need to have a huge justification for why you're using it. And even then, people might still get mad at you, and they might complain. Remember that all the publications has to go through peer review. So your peers are going to say, why are you doing this? And they might make you change it. The reviewers. So it's probably best just to stick to a two-tail test as a default. So here's the same graph I showed you before, but in this situation, we've increased the sample size from 4 to 25. And as you can see here, there's a big difference now. Look at how spread apart these graphs are. Now, these graphs are more narrow. They don't look more narrow, the curves, but they are, because look at the x-axis. It's more spread out. So they kept the curves the same size just to show you that they don't overlap. But these distributions are much more narrow because the standard error has gone from 5 to 2. They just changed the scale on the x-axis. They spread it out more. See how they don't overlap now? So the distribution that represents the null hypothesis on the left does not overlap with the distribution that represents the sample, which is part of the alternative alternative population, right? they don't overlap. So since they don't overlap, power goes up. So here power is much higher. It's probably in the 90s, right? Because 90% of this curve is shaded as opposed to 30% of the curve before. Here you have 90-something% of the curve on the right shaded. You only have that little tiny piece on the left tail that's not shaded. It's almost entirely shaded, so it's like 90-something% power. This is the ideal situation. And how did they get to this situation? Well, the effect size was the same. The effect size is still 8 points, right? There's 8-point difference. But the sample size increases. So this just shows you how powerful the sample size is for finding statistical significance. It doesn't affect the effect size because the effect size is the same, but it affects the statistical significance greatly because now you have the two distributions that don't overlap at all just by increasing the sample size from 4 to 25. And if I increase the sample size even more, the curves are going to be even further apart. So any difference, any effect size is going to look much bigger. You know, any difference between these two means is going to look much bigger when I increase the sample size. So just keep pumping them up, but don't abuse it. So don't, 500, 1,000 people, that's overkill. People are going to be suspicious. They're going to ask you for effect size measures. But if you keep it at 100, 200, people won't be that suspicious, and you're going to get a better result. You're going to have a much more powerful study. Just don't abuse it. I've seen studies with 5,000, 10,000. I get really suspicious when I look at 5 or 10,000 as a sample size. I don't want to see these curves because these curves are almost by default going to be different. I want to see the effect size because even a tiny effect with 5,000 people is going to look huge. It's going to be statistically significant because the sample size is going to drive these curves. It's going to increase power so much that these curves are going to be completely separate, even a tiny, tiny effect. So if you have a huge sample size, be careful because people are going to start asking questions. They're going to say, is this really a big effect? Is this something I should pay attention to? Or is it because you have 5,000 people that you have such a huge difference? And if it's the latter, then you need to show them the effect size. And the effect size is like 0.00 something. It's close to 0. Now they're not going to take your research seriously. They're going to say, there's really nothing here. You just, boosted it up with the sample size. You're saying statistically significant, but that doesn't mean that it's important. So that's another thing. Statistical significance just means that it's not due to chance. It does not mean that it's important. People conflate the two. They think that if it's statistically significant, it's important. It's not. It could be. If there's a large effect size, it's important. But if there's a really tiny effect size and it's statistically significant, then the effect is not important. The manipulation, the intervention is not really powerful at all. It's not something to even really look at. But yet people try to publish with this, with these huge sample sizes. So be careful with that. Last couple slides. The power of a statistical test is the probability of rejecting the false null hypothesis, right? So it's the probability of correctly rejecting the null hypothesis. When I say correctly rejecting, that means that the null hypothesis is false, right? And you need to reject it. So it's rejecting the false null hypothesis. That's the same thing as saying correctly rejecting the null hypothesis is rejecting the null hypothesis when it's false. Cohen's d is used because alone a hypothesis test does not measure the size of the treatment effect. Well, it doesn't. Statistical significance just tells you if it's due to chance or if it's due to the effect of the independent variable. It does not tell you how strong the effect is. So hypothesis testing only tells you chance or not chance. It doesn't tell you important. So Cohen's d answers that second question. It tells you whether it's important. And lowering the alpha level from 0.05 to 0.01 will increase power. Well, obviously not. Every time I lower alpha level, I decrease power. I make it harder to reject the null hypothesis, to correctly reject the null hypothesis. And that's what we got here. So there's a lot going on here. Take your time, walk through it, digest it, read the text, watch the lecture again. I tried to explain it the best I can explain it, especially given the remote learning modality. If you have questions, reach out to me, email me, stop by office hours. You need to really make an appointment for office hours now because there's advising, and you combine that with office hours. It's just, there's too many people. So I've set up a schedule for office hours, make an appointment if you need to see me. And if you can't make those times, let me know, and I'll try to squeeze you in some other times. But see if you can make those office hours. Email is good. Let me know your feelings on it. If you have questions, I'll try to explain it in a different way if possible. But take your time and digest the material and work through the problem set in the book for the homework. So hopefully that helps. Bye for now. See you next time.